This example comes out of section 1.2, limit of a function. In this question we're asked to find the limit of x minus 3 over x squared minus 4x plus 3 as x approaches 3. To write that, I wrote it in words, but to write it in symbols, the way we will throughout the course, is the limit as x approaches 3 of this particular function. Now, the first thing I think is, well, if this function was defined at x equals 3, this would be a piece of cake. I just put in 3 and see what it equals. If you try that, you're going to get a problem, because you're going to get 0 divided by 0. And the 0 divided by 0 problem is a real common calculus problem. You run into 0 divided by 0 quite often. Some people call it indeterminate form. But basically, if we run into 0 over 0, we're going to have to do something to change what this limit looks like. Now in this case, the steps are relatively straightforward in that we're just going to factor everything that we can. The numerator is already as simple as it can get, but the denominator can be written as x minus 3 times x minus 1. Now, that has two non-permissible values. X can't equal 1, x can't equal 3. But we're not talking about when x equals 3, we're talking about the limit as x approaches 3. And so the smartest way to go about doing this is to then say, well, that means the limit as x approaches 3 of, cancel out the common factor top and bottom, 1 over x minus 1. Now, if my function was 1 over x minus 1 to begin with, I could have just put 3 in it right off the bat and said this answer is 1 over 2. And so that is one of your main techniques of solving a limit, is to factor and then substitute in the number. If we didn't have that skill, we'd be stuck doing something like this, saying, okay, well, if we're trying to find as x approaches 3 and we have the function x minus 3 over x squared minus 4x plus 3, we're going to need to try numbers really close to 3. So, we might try, let's let x equal various numbers really close to 3. Like, for example, make a table of values here, 2.5, 2.9, really close, 2.9999, get carried away here. And if I put in that number into this function, let's call this function f of x for a second, just so I can say, well, what does f of x equal? If you put in 2.5, you get 2/3 as your answer. You get 0.666666. If you put in 2.9, you get a slightly bigger number. You get, smaller number, 0.526 something, more decimals. If you put in 2.9999, which, if I was trying to graph this, I can't even tell the difference between 2.9999 and 3. I get an answer that is just 0.500025. Now those are all numbers that were just smaller than 3, so let's try some numbers that are just bigger than 3. So for example, if I were to put in 3.5, well, what does this function equal when I put in 3.5? And I get 0.4 exactly. Now if I tried something even closer to 3, like 3.1, again, 1/10 the way, I get something like 0.476 decimal. If I put in 3.0001, 1/10,000th of a unit away, I get 0.499975. So if I were to present you with these tables of values and say, like, let x equal numbers close to 3, and said, what do you suppose this limit equals? I think even without understanding the factoring step or anything like that, if I do x minus 3 over x squared minus 4x plus 3 and say, well, put in numbers as close to 3 as you can get, if I look at this answer and this answer, it sure looks like the answer to this limit is about 0.5. So at that stage, it's a guess, and this is kind of the educated guess, whereas up above we actually have a bit more of a concrete method where we factor and find that spot. If you took Math 30-1, you've run into this when you found points of discontinuity. If you actually looked at the graph of this function, it has an asymptote at x equals 1, it has kind of a curve, something like roughly like this, and a curve like this, but at x equals 3, there's actually a hole in the graph. You'd have to zoom in real tight if you're looking at a calculator, but the hole happens at 3 comma 1/2. So hopefully you're at least a little bit familiar with this if you did take Math 30.